So similar to how we combine resistors in series and parallel, we can also combine capacitors in series and parallel. In this video, I'll show you the rule for combining them in series and parallel, and I'll also solve an exercise to show you that. So first, I'll start off by connecting capacitors in series. And just as a quick reminder, in series meaning a couple capacitors share one node, and this node is not shared by anybody else. So a couple of this capacitor and this capacitor share this node. This capacitor and this capacitor share this node, and as it turns out to be that these three capacitors are in series. And of course, if they are in series, they do share the same current, but each one of them will have its own voltage, and that's what you see in here. So in this example, what I'm interested in is three different capacitors, C1, C2, and C3. They have these particular capacitance, C1, C2, C3, and each one of them will have an initial voltage of V1 T0, V2 T0, and V3 T0. Initial voltage meaning that initially each one of them will have its own stored energy, and of course they do share the same current. So what I'm interested in is replacing these three, but by their equivalent capacitor, C equivalent. And of course, I'm also interested into the voltage, the initial voltage that is stored across this equivalent one. So how do we get started? Well, first of all, if you remember, what we're interested in is maybe V, which is this voltage across here and here. If we write KVL, we should be able to tell that it's simply V1, and these are all functions of T, of course, plus V2T, plus V3T. And we know that V1 of t, okay, is just simply 1 divided by C1, the integral from T0 all the way to t, and that will be I of tau, d of tau, sorry, plus V1 of T0. That's from the rule of how the voltage, how you can get a voltage if you know the current. So we know the current in here. We're going to assume that we know the current in here since they share them. This is how we get the first voltage. And you can repeat the same thing for V of 2. And what you will get is 1 divided by C2 and T0 plus T in here. And that will be I. It's the same I, d tau, but different initial voltage. So that should be V2 T0. And then V3 of T, that will be simply 1 divided by C3 from T0 all the way to T, I of tau, the same I of tau, d of tau, because they share the same current, V3 T0. Alright, so these are the three ones. So if I actually combine these, for example, basically I substitute the value here for V1, the value here for V2, and the value here for V3, what I'll end up with is the following. I'll end up with something similar to 1 divided by C1 plus 1 divided by C2 plus 1 divided by C3, and all of them are multiplied by T, T0 to T integral of I of tau, d of tau. Okay, and then also all of them will be added to V1 T0 plus V2 T0 plus V3 T0. All right, that's what we will have, and I can put these in square brackets, and that will be the V of 2. All right, so this is what we get from this particular circuit in here. So let's do the same type of analysis for this particular circuit in here. So if they're equivalent, of course, they will have the same exact voltage and the same exact current if these two combinations are equivalent. So if I write this equation, I'm going to just write it in a different color in here. So V of t for the second circuit, which is here, is simply 1 divided by C equivalent times T0 to T I of tau. It's the same I again. If they're equivalent, they should have the same I. Okay, that's the same tau, and then d of tau plus V of T0. And of course, let me just highlight it in here. If you compare these to that, you will end up with the rule of how we combine capacitors in series. So capacitors in series, so 1 over C equivalent equal 1 over C1 plus 1 over C2 plus 1 over C3. And if you have more, all you have to do is just basically take the reciprocals and add them. And similarly, we can compare this here, this V0, 1, 2, 3 to this V0, and you will realize that pretty much that the initial voltage across the equivalent capacitance is just simply the initial voltage across the first one plus the initial voltage across the second one plus the initial voltage, well, T0 plus V3 T0 all the way, and if you have several of them, it'll be Vn T of 0. So to summarize, combining capacitors in series is pretty much similar to combining resistors in parallel. So capacitors in series is in the same way that we combine resistors in parallel. All right, so let's do the same type of analysis, but now instead of connecting them in series, we connect them in parallel. And of course, in parallel, that means each one of these capacitors will share a pair of nodes. So these two in here will share these two pair of nodes, these two pair of nodes, and as it turns out to be the C1, C2, C3, they all share the same pairs of nodes, so they're all in parallel. And what I'm interested in is replacing them with a single equivalent capacitor in here. Of course, they do share the same V in here and the same V in here. They don't share the I's, so let me just highlight them in here. So what we have is we will have I1 of T, of course, and then we'll have I2 of T, and then we'll have I3 of T. Okay, but in terms of the initial voltage, since they're all in parallel, that means they share the same voltage, so they will have the same exact initial voltage, and it will be the same exact initial voltage across the equivalent. So the only thing I'm interested in is how do I combine the C1, C2, C3 to get the C equivalent. And the rule again is pretty simple. So what we have is we have I1 of T is just simply C times dV T divided by D of T. Of course, that will be C1. All right, and I2 of T is just simply C2 dV T divided by dt in here, and then the I3 of T is just simply C3 dV of T, and again, all of these dVs are the same because they're in parallel. All right, and of course we would know based on if you write KCL in here, you'll end up with that I is simply I1 plus I2 plus I3, and if you do the algebra, you'll end up with C1 plus C2 plus C3 dV of T divided by D of T, and that will be the I of T. All right, so if you write similar equation, but now for the equivalent resistor, what you will end up with is that the I of T, which should be the same, if they're equivalent, this I and this I should be the same, is just simply C equivalent times dV of T divided by D of T. And I'll highlight these two in here, so by comparison, you will realize that simply the C equivalent is just C1 plus C2 plus C3, and if you have more capacitors, all you have to do is just combine them, just add them. So combining capacitors in parallel is very similar to combining resistors in series. So these are the two rules for connecting capacitors in series and in parallel. So let's solve a quick exercise just to see how we can use these and apply them in practice. So in here I have this particular combinations of capacitors and just capacitors for now, and what I'm interested in is the total capacitance seen from these 2 points in here, these 2 terminals. Okay, so I would recommend that you pause the video and just try to do it on your own, and then come back and see how I solve it. So first I'll identify in here like that this node is shared between this 1 microfarads, 2 microfarads, and 3 microfarads, and all of them also share this node in here. This is the same node. So as it turns out that the 1, 2, and 3, they're all in parallel, and of course we can combine them. Of course capacitors in parallel can be combined similar to how resistors in series are. This is how I remember it. It's the opposite of resistors. So all you have to do is combine them. And I'll redraw that circuit in here. So it will be 1 plus 2, which is 3, plus 3 is 6 microfarads. So we'll end up with something like this. Okay, that's 4 microfarads. And then it's combined with pretty much 6 microfarads in here. And then we still have this one in here, this one in here, that will be C of T. And the 12 microfarads are still the same in here, that's 12 microfarads. Of course, now hopefully you recognize that these two are in series, and of course if they are in series, what you have to do is you have to combine them, basically you just have to combine them similar to how resistors in parallel are combined. So let's do that. So what we have is the combination here that are in series. We simply figure out the equivalent capacitance, that's 6 times 4 divided by 6 plus 4. Okay, and that's 24 divided by 10, which is 2.4 microfarads. That's basically the combined. And we can redraw it in here, and what we will get is C of T, and that here will be in here, and these two will be in here. That will be 12 microfarads, and that will be 2.4 microfarads. All right, so the combination now is simply, now I have this, and these are in parallel. So C of T is just simply 2.4 plus 12, and that will be 14.4 microfarads.